Great. So we are here to talk about developing reasoning skills in the foundation phase classroom, because I think we can all agree that in this day and age of so much information at our fingertips, and being able to access information so easily, it has become more important than ever to be able to reason through that information. And I think the global trend is following the same kind of thinking. We need to create thinkers out of our learners. And there's been this global trend towards a shift in 21st century education. And I'm not sure if you've come across this phrase, you probably have, but what it speaks about is it tells us to go beyond traditional rote learning and start focusing on creating critical thinkers in our classroom. And to do that, we need to create opportunities where the learners have real world problem solving, they have critical thinking and reasoning skills that are being developed, they collaborate and they communicate, they talk about their solutions in the classroom. And the learning is very student centered, as opposed to the teacher just, filling them up with all these facts and information. The learners are actually discovering and exploring, and they are creating or constructing their own knowledge from experience. There's also a strong focus on conceptual understanding, which supports the inquiry-based principles that we all know of. And what does this mean for the classroom? So I think what we need to remember is that this kind of approach is going to create learners that can solve problems because they understand things deeply and they can make sense of it. And in terms of mathematics, it means that they can use mathematics to solve problems in their everyday life as well as in the classroom. 21st century education also advocates sense making over memorization, and it's more a focus on understanding why the strategies work, so that you can use them in unfamiliar contexts. And then it also encourages an element of productive struggle. And I like to think of the analogy of the butterfly. So when the butterfly is in a cocoon and it starts emerging or it breaks free, the fluid starts pumping into its wings and it starts breaking free from the cocoon. And this struggle that the butterfly goes through is actually strengthening its wings so that it can take flight and be able to fly. So in the same way, we need to get the learners to struggle just a little bit within reason so that they can start progressing and evolving beyond where they are. Another element of 21st century education is the fact that learners can explain and justify and discuss their thinking with their peers. And through talking through one's thinking is how you actually develop your reasoning skills. Another hallmark is the fact that there is more than one way to skin a cat, and the same is true for the mathematics classroom. Exploring and talking about different ways of solving problems and performing calculations is just developing reasoning in another format. Connected learning is another hallmark that we will speak a little bit on later. And what this means is that we build on the knowledge that the learners already have, and we connect the ideas so that they can apply their knowledge in different situations to solve their problems. And lastly, the teacher acts more as a facilitator as to a lecturer, if you will. So it shifts from not just telling facts and formulas, but the teacher starts asking questions to prompt thinking so that the learners are guided towards exploring or discovering some new insights. So I touched on it a little bit earlier, but mathematics, to me, is the language of science. You cannot do or access any scientific field without having a robust understanding of mathematics. No scientific experiment is complete without the mathematics. There's always some number element to it. There's some data that needs to be crunched. There's some observations that needs to be justified. And I think mathematics is just so crucial in scientific discovery. So I'm going to stop chatting to you for a second, and I'm going to encourage you to pick up a pen or a pencil, and hopefully you have a jotter nearby. And I'm going to ask you to do this calculation in any way that makes sense to you. I've got a timer here for 60 seconds, but perhaps what we can do is we can extend it so that you can solve it and then maybe also share in the chat a few of your solutions or strategies that you've used. Okay, so the timer is going to start now, and then we can have a look.
But it tries. Okay.
Should do long division.
Okay, so my timer is now at 0. Just ignore that it's starting again. But perhaps we can just have some people share some strategies that you used. Maybe, what answers did you get? Is anybody willing to share?
Please feel free to unmute your microphones, colleagues, and share.
Thank you. I'm sorry, I can't see the chat either, so
Maybe you can turn on the Q&A, Younger, for those using the app to be able to text in there.
Okay, sure.
okay. So let's have a look. Perhaps you were one of the people who resorted to the trusty long division. We all know this. We learned this at school. We know the steps, and we would have just jumped right in and applied our steps. Hopefully, we could remember the correct order in which to do it. And as a bonus, hopefully, we understood why we did what we did. But if you followed the prompts for the long division algorithm correctly and in the right order, then you would have come up with the answer of 955. And there we go, that's the end of that. Perhaps you reached for some technology and you just used your calculator, which is actually very reasonable because we all have a phone and we all have a calculator, probably somewhere on our phone that we could just reach for and use. I think the reason we're showing you this is because we know we've got so many platforms where we can perform calculations. We don't need to be able to perform calculations as as was the need some years ago. We have tools to do that for us. What we need to start doing is we need to start making sense of the numbers, and we need to realize as teachers, and we need to also get the message across to the learners that mathematics is so much more than just numbers and getting the right answer. It is a beautiful tool that we could use to solve problems, both in everyday life, but also, as I said earlier, in school. So what would someone with this kind of thinking have done had they had the same calculation? Well, they might have thought of it like this. 2,865 cannot divide by 3 that easily, but what I do know is that 2,700 can. So if I break up the number and I then divide the two parts separately by 3, so 2,700 divided by 3 will give me 900, and 165 divided by 3 will give me 55. If I put those two back together, I will get my answer of 955, which I am 100% sure is correct because all three of these get 955 as well. So this is just an illustration of what it would look like if you were making sense of the calculation and the numbers. And what we're trying to do is we're trying to move away from the school of thought where we would memorize facts and rules and formulas and try and foster a more sense-making approach. So we want maths to be meaningful and it needs to be a problem-solving activity. So we're kind of moving away from mathematics as just being calculating to it being calculating, but with understanding so that we can apply it and then use it as reasoning as well. Because we also note that children who are taught mathematics as rules to be remembered, they very soon give up. So they just don't try to make sense of it any longer because they have this crutch that they can lean on. But we need to change the focus. We need to change the focus from just getting the answer to asking how did you get the answer and why did you do that? That just makes the experience more rich. So if I can illustrate with an example, here is a problem from our series. So 5 friends share 6 chocolate bars and 3 friends share 5 chocolate bars. Show them how to do it. Here's an example of a child who has suspended all sense making. This child has taken the two numbers from the problem, 6 and 5, and they've chosen one of their 4 operations, whether it's plus, minus, times, divide. I suppose they just had a guess at which one, and they plugged in the numbers and they solved. This doesn't make any sense. And again, the child repeated the same mistake, took 5 and 3, and he got the answer of 2. Everybody gets 2 chocolates. This is a clear example of somebody who's not trying to make sense of the problem. Here's another illustration. We're going to double 38. This learner wrote down his or her 38. They're going to double it, which is great. So then 3 doubled would be 6. So far, so good. 8 doubled, that's 16. And this child was perfectly happy just leaving it in this way, not trying to make sense of the fact that 38 is equal to 616. A clear example of somebody who's been taught a procedure, but they don't understand what the procedure is doing. And in that sense, they applied the procedure incorrectly. A lot of the work that we do is pinned in the research from this body of work. It's called Adding It Up. And in this body of research, they speak about the 5 pillars of mathematical understanding. And we've just shortened it a little bit. And we've said that not just knowing is not enough. We need to know with understanding so that we can apply in unfamiliar situations and we can reason through our thinking. And the short story of this is that success in mathematics relies on understanding and what you are doing. And it is so much more than just getting the right answer. Which brings us to reasoning. Reasoning skills are foundational to any kind of learning. including doing maths. And more generally, it's what makes us human, because when we reason, we use the knowledge that we have to learn to be better and to solve critical problems. But how do we get the learners in the classroom to develop their reasoning skills? We advocate to give them problem-solving strategies. So if they don't know what to do, then what do they know? What can they do to get themselves unstuck? Well, if they don't know what to do, will acting out the problem help? Will drawing a picture help? Could they look for patterns? Could they just simply guess and check? Could they work backwards, make a list, make a table, solve a simpler problem? And eventually, they will be able to write an equation because they've gone through the process of making sense of a concept. And just to be clear, we're not opposed to the fact of using an algorithm or writing an equation to solve a problem. We just don't start with that. So I think writing an equation, using an algorithm for the higher grades is very appropriate. But when we are in the foundation phase, we need to first get a robust understanding of what it is we are dealing with, of the concepts. So calculating with understanding, applying, and reasoning is so critical, because anything less leads to knowledge that is fragile, disconnected, and weak. And I'm going to use an example to illustrate what we think fragile, disconnected, and weak knowledge looks like. And the example is 17 take away 8. I don't know what 17 take away 8 is. So I jump right into my column arithmetic because that's what I know I have to do. But if you look at what's happening here, I end up right where I started and I'm stuck. But if I have a solid understanding of number and I can calculate with confidence, then I can make a plan. This child drew a number line. If I add 2 to 8, I get 10. If I add 7 to 10, I get 17, which means the difference between 17 and 8 will be 9. I've made a plan. Somebody else might have made a different plan. This child said, I know what 10 take away 8 is. It's 2. So then 20 take away 8 must be 12. And then I can count down from there and know that my answer is 9. Yet a different way is to just take 7 away from 17, which is 10. So that means 17 take away 8 must be 9. I've reasoned through the calculation. And this is what we are trying to develop in our classrooms. We want to support children in experiencing mathematics as a meaningful, sense-making, problem-solving activity. And one area where we can do that is in our mental arithmetic starters. Performing calculations consists of 3 parts. First, it develops a sense of number, or it needs a sense of number in order to perform calculations. And to develop that sense of muchness, we do counting activities. Then we need to understand the meaning of the operations, plus, minus, times, divide. And we do that by posing problems to the learners which they can solve using their knowledge. And the third puzzle piece is to have a critical mass of number facts. And basically, that is your mental arithmetic skills. Or do you have a critical mass of number facts that you can use to perform your calculations? Let's have a closer look at the mental arithmetic part of this. Again, I'm going to ask you to do this calculation in any way you want. So grab your pen and paper and please solve that one. And I hope this time somebody will share. Okay, 5, 4, 3, 2, and 1. Anybody wants to share a strategy that you used? Okay, well,
I can go for it. Oh, there is Shahima. Whose
okay,
hand is
great.
up. Thank you,
Thank
Shahima. You can go ahead.
You're welcome. Good afternoon. Apologies, can you hear me?
Yes,
Yes, we can.
definitely.
Okay, so what I did was I firstly said 200 minus 100 is 100, and then the 100 that I've got left is 100 minus 80 is 20. So then I'll take that 20, add it to my 40, which gives me 60. 60 minus 7 is equal to 53, and then 53 plus 8 is equal to 58.
Wonderful. Well done. That's awesome. Great. Did
Thank you.
anybody do it in a different way? Sinovuyo.
Sinovuyo. You can unmute your microphone, Sinovuyo, and go ahead.
Looks like the microphone is faulty because we can't hear you. Perhaps you are welcome to maybe send me a message on our WhatsApp line, or you can use the Q&A, which will be on top if you're using a app on a PC, and on a phone it will be there at the bottom.
Okay, great. Thank you, Sinovuyo. Perhaps we will come back to your strategy when we have the solution. Novosti, you'll just give me a buzz when his solution comes through.
Yeah, sure.
Thank you. Okay, so perhaps you did column arithmetic. And if you did, I hope you noticed that the trauma with this particular calculation is the fact that there's a double borrow. And for little ones, it can be quite dramatic and the room for error is quite huge. However, if they are flexible with their numbers and they understand the concepts, then they might have thought of it as a number line, like we did before. So if I add 13 to 187, then add 45 to get to 245, then I will get 58. So the point here is I don't have to subtract in order to calculate a difference. I could also use my knowledge of addition in order to do that. Here's another calculation. And what we're going to do is we're going to analyze this one. So I'm going to give you the answer. It's 1,222. And I'm going to provide a specific solution. And then we're going to have a look and see all the different skills involved in performing this particular calculation. So this person started off by saying, how much do I need to add to 768 to get to 800? Well, they thought of a number line, just as the others, and they determined 32. Great. The next step, or the next question they asked themselves was, now, if I have to add 454, but I've already used 32, then how much more do I need to use up 454? So that means 422 plus my 32 would give me my 454. So together, I would say the 800 plus the 422 would give me my answer. So this was their particular thinking. And for the intermediate phase teachers who are here, you would recognize this as being rounding and compensating. But in terms of foundation phase, by doing these calculations, we are making sense of it. It doesn't have to have a name, but we know what we are doing. So let's unpack the strategies that we are dealing with over here. In order to have done the first calculation, I must have known that 700 plus 100 must give me 800. And before that, I must have known that 70 plus 10 is 80. And my critical number fact that I know is that 7 plus 1 is 8. So that's the start of it all. That is in foundation phase where we practice these number facts so that one day we can perform higher level calculations. What I also needed to know was to complete the 10. So 68 plus 32 gives me my 100. But before I knew that, I had to know that 68 plus 2 gives me 70. And my critical number fact that I used was the fact that 8 plus 2 is 10. In the same way, we can think about the other calculations. So 400 plus 54, that's just straight place value. For the next part, we have 32 plus 22 gives me 54. And to do that, I needed to be able to say or know that 30 plus 20 is 50. And my critical number fact, 3 plus 2 is 5. We also had to know that 2 plus 2 will give me 4. I hope you see where we are going with this. We are going to focus on the critical number facts that we can apply in unknown situations. For the last one, again, to do 800 plus 400, I had to know first what 80 plus 40 was, and before that, I had to know what 8 plus 4 was. And lastly, 1,200 plus 22 will give me that because I know that 22 plus 100 is 122. And my critical fact is knowing that 10 plus 2 will give me 12. So that's the thinking or the history from where I've come in order to perform this calculation. And the strategies involve place value. I see your hand, Navasti. I will be with you in a second. Place value, single-digit arithmetic. For these two calculations, I had to know single-digit arithmetic in combination with arithmetic with multiples of 10. Right at the bottom, that is similar to place value. It's adding to multiples of 10. We have completing the 10 up there. And then lastly, this one needs to be able to bridge 10s in combination with arithmetic with multiples of 10. So I hope you can see how many skills have been developed to get us up to this stage of thinking. Yes, Navasti.
Thank you. So we've been having a conversation here with my colleague Rose sitting next to me.
Yes.
And we just made a realization of how we have become so automatic with doing things as adults to the extent that we actually tend to turn a blind eye on the basic things, thinking as adults in terms of what perhaps will be helpful to help a child understand and reason with numbers.
Be able to get to this.
Things just happen intuitively because we're adults and our brains are used to it.
Yes, and also you've gone through the journey and you've kind of, you know what works. And it's almost like a shortcut. You just want the learners to also know what works, but they need to actually go through the journey as well.
Absolutely.
Nice. Thank you. Thank you for the comment. Anything else?
Okay, yeah.
I'm sitting next to Navosti. I think doing a chart like this is very revealing for us as a teacher to say, oh my word, children have to know all these operations and understanding number line and understanding how to work with tens and units in order to do a calculation like this, which we would probably be able to do, in one step. But they need all this foundation before they can do something like this.
Exactly. Exactly. And also, I think as adults, we need to remember that maybe not these calculations, but some kind of calculations, multiple calculations, are happening in your mind mentally to solve or perform this calculation. So there's a lot of thinking involved. Okay, shall we move on?
Yep, there
Okay.
not any hands that are up. And
Okay.
if you've got any question, colleagues, please feel free to unmute your microphone and ask or say a comment.
Absolutely. Thank you very much. Okay, so what does this mean for the classroom? It means we need to provide a lot of opportunity for the learners to practice these skills, which include single-digit arithmetic, arithmetic with multiples of 10, adding, subtracting to multiples of 10, which is your place value type questions, completing tens, bridging tens, and then doubling and halving with multiplication facts work hand in hand. So there's a lot to learn and a lot to understand. What it also means is place value needs to be understood, not just in terms of 500 plus 70 plus 5, but it also needs to be understood in various different forms. So it could mean any of these. And do the learners understand that this all builds up to the same number? We like to use the analogy of the critical mass of number facts in terms of reading. So we like it to reading in the fact that it's sight words. When we learn to read, we develop our sight words through reading. We read books, we read stories, we just read as much as we can. And in that way, reading becomes automatic. And in the same way, the number facts need to become automatic at some stage. But we also have to have an element of understanding. So we are not just memorizing, we are understanding and we are using it so often that it becomes our sight words. It becomes automatic. And research has indicated some kind of mental arithmetic activity every day in the classroom actually enriches the classroom setting and enriches the understanding of mathematics. So what we have is we have a little mental mathematics book with lots of different start activities, and the questions are structured in a way to reveal the connection. So we're teaching the learners that if you don't know how to do something, so for example, if I don't know how to do 59 plus something gives me 60, well, if I know that 9 plus 1 is 10, then I can use that to solve the thing that I don't know. And we are very deliberate in structuring our questions in this way. Here's just another example of structuring it like this. And you would see or notice that we stop and we have prompts where we encourage the learners to share the patterns that they see so that they can make the connections themselves. Here's another example, and that's just showing the connection or the pattern with when we times by 10. Okay, we have the lesson starter, but in our actual workbooks, we have similar activities that do the same thing. I'm going to show you this one, and then perhaps we could have a few comments from the teachers. If this is the activity for the day, and we've deliberately structured the questions in this manner, what do you think we are trying to reveal to the learners? What do we want to show them here? Any thoughts around what you think we want them to learn from this?
Multiply by 5 and multiply by 10.
Yes. And what do you notice between the answers of 3 times 5 and 3 times 10?
But they're doubling.
They are doubling. And if you look at the next one, 6 times 5 and 6 times 10 is also doubling. So what we're showing them is if I can times by 10 and I can halve, then I can also times by 5. Nice. Good. Well done. So that is if we look at the relationship horizontally, but there's also a relationship going vertically, which is also doubling. So if I say 3 times 5 and I double it, I get 6 times 5. And if I double 6 times 5, I get 12 times 5. And then the last one, well, I just have to add one more group of 5. And in this way, these patterns show the connections, and it makes the learners, it gives them the ability to solve problems when they don't know something. They can use a fact to help them solve a different item. Okay. So having a sense of number is having a rich understanding of the meaning of number, but also being able to work fluently and flexibly with our numbers. Just as the learners were in our 17 takeaway 8 example. And what we like to say is that we want to build a toolbox of strategies. So we want this toolbox to be filled with lots of different ways and strategies of performing calculations. And then having the learners learn or realize when to use which strategy, because we don't want them to be one-trick ponies where they only use one strategy to solve all their maths. We want them to be selective and choose the appropriate strategy for a given problem or calculation. And to show you an example of a classroom where this is successful, I've got a little video. I hope the sound works, but otherwise we'll just talk through it. The problem was there are 16 children in the class and they each bring 50 cents to school. How much money would that be? And this is what was delivered.
No sound.
I think you didn't include sound.
Stella.
Okay, let me repeat that. So the first
Hi,
child.
Stephanie.
Yes.
There wasn't sound on our side.
Oh.
Maybe it would be helpful to include the sound before sharing.
You know what? I'm actually not going to attempt to do that because, oh, there's the share sound. Okay, wait, let me go back. Let me go back and then I will try again. Wait. Okay.
Cents is 1 rand.
There we go.
So 50 cents plus 50
What?
cents is 1 rand. So I counted from 1 rand to 8 rand because it's half your 60.
Very good, Daniel.
So, you know, 10 of 50 equals 500, and then you half that equals 250.
For the
so
5
then,
extra.
Yes, so then you got 15, and so then you got 1 left over, and so that's 50, so I got 800.
Excellent.
Nice.
Smart.
Thank you. Okay, so I'm going to talk through it because the quality is not that great and they talk quite quickly. So the first child said, I don't know what 16 times 50 cents is, but I do know that 16 times 100 cents is 16 rand, and I know that 50 cents plus 50 cents is 1 rand. So that means if I half this, I will have my answer of 8 rand. Then child number 2 said, I don't know what 16 times 50 cents is, but I do know what 10 times 50 cents is. And if I halve that, it means I've got 5 50 cents. So if I put that together, I've got 15 50 cents. So 15 50 cents would be 750 cents. And then I just need one more child to bring a 50 cents. And I would have my 16 50 cents. So that means I get 8 rand, just like my friend. So this is an example of being able to work fluently and flexibly with your numbers. And that is what we are trying to foster through deliberate, structured, and developmentally appropriate routines. To illustrate that, I'm just going to quickly show you how we can learn the times tables through understanding as opposed to just memorizing. So if we can agree the times 1 times table is for free, and we should all be able to get that one. Next, we get times by 10. And that one's pretty easy because if I see the pattern of just adding a 0, I've got it. And it doesn't just limit me to 12 times 10. I can, once I've seen the pattern, I can do 24 times 10. I can do 35 times 10. I can do anything times 10. Then, as we saw before, if I just halve my 10 times table, I will have my 5 times table. And then as an added bonus, I can do what the child number 2 in the video did. I can add my 10 times table and my 5 times table, and I can then also times by 15. Next, let's just look at an example. So 5 times 3 is 15. 10 times 3 is 30. And then that means that 15 times 3 would be 45. So I can just add those two. Next, I can double. So if I can double, I can times by 2. Then I will be able to times by 4 because I can just double twice. Double is the same as times 4. And by the same vein, I can then times by 8 because then I can just go double, and double again. In fact, I can also do times 16 because then I can just, I think you get the idea. We just double 4 times. Then we are in a position to combine. So the 3 times table, maybe a little bit of counting in threes. Maybe I can times by 2 and then add one more group. But once I can times by 3 and I can double, I can get my times 6 table. And for times 7, I can combine. So for example, I could take 5 times 6, which is 30. Sorry, I'm doing 7. 5 times 7, which is 35. And 6 times 7, which is 42. And then I can add it together and get my answer for 11 times 7. Times by 9 is also very accessible because I can times by 10 and then just take away one group of what I'm timesing by. And then by the same vein, I can times by 11 by just adding one more group, times by 12, times by 10, and then add 2 groups, etc., etc. And in that way, I've made sense of the entire 15 by 15 times table grid without having to memorize it. But just to echo what I said before, we do want this to have an element of being automatic. And by using these facts often and regularly, they will become automatic. Yes, Navosti.
It's Rose here. Would you use this as an exercise for children to do?
No,
what you've just done.
I would not. I would bring it out in discussion. So I would set up a pattern just like I showed you before, where we had the 3 times 5 and then the 3 times 10. And then I would ask them what they notice. And then I would draw out these thinking skills in the discussion.
Okay, great. But then this is a very nice thing to, if you have 100 squares, say, on your table, then your times table becomes very easy because you just go down one group and across the other, and you can find the answer. Yeah. Thank you.
Thank you for the question. Okay, so again, we link back to knowing with understanding, applying, and reasoning. And then reasoning is also at the heart of solving problems. And we use the problems in the NumberSense series for 3 reasons. First, it's to introduce the learners to different situations so that they know the meaning of the 4 basic operations. They play a role in developing calculation strategies. And lastly, it becomes something that they can use on an everyday basis to solve problems. So I'm going to pause here once more, and I'm going to ask you to solve these 2 questions. So Mrs. Thing needs 2/3 of a cup of dates to make 1 muffin. She wants to make 3 muffins. So how many cups of dates does she need? And the second one, she has 2 cups of dates. How many muffins can she make? Okay, how did that go? Are we done? Okay, so let's have a look. In essence, what we are asking learners to do is to
Yes.
work out what 3
Yes,
times
of
2.
course.
Pardon? Pardon?
Okay, you can respond.
No, we were just laughing because we're comparing results.
Oh, fabulous. Would you like to share with us?
Yeah, we can.
Okay. Yeah.
So with the in terms of how many cups of dates does she need, we found that she would need 2 cups of dates.
Okay.
Then we realized that the second question is actually the same.
Yeah.
Okay, it actually has the same as the first part of the question,
Yes.
which is 3 muffins. Yeah.
Yes. Yes. Good. So it's the same question, but it's asked in 2 different ways. Well noted. Good. So basically, the first one is wanting the operation of 3 times 2/3. So there's lots of different ways that you can solve this. But this problem has been introduced at a time when the learners are not able to multiply with fractions. So they have to make a different plan. They have to make sense of the situation. And drawing a picture is at this level what is expected because it's the first time they come across something like this. So there's the 3 muffins. And if I cut this up into thirds, I need 2/3 for that muffin. Similarly, I need 2/3 for this one. And I need 2/3 for the red one. So perhaps to make sense of that, I can fill up this cup with all my thirds. That's 1, 2, 3/3. And then I can fill up that cup with my remaining 3/3 that I have. So basically what we need to know is that we have 6/3 and that the 6/3 will make 2 cups. And for the second one, we are dividing. We're taking the 2 cups and we're dividing it into the muffins. So we want to work out how many muffins we can make, sorry. And to do that, the picture is going to have a little bit of a different feel to it because the sense making is different, or the thinking process is different. So there's my cups. I've got 2 full cups, which I'm going to use to make my muffins. I will use 2/3 for this one. And then I will use 2/3 for that one. And then for the last one, I will use the last 2/3. So the problem that is posed elicits a different drawing, and that is how they make sense of it. So to illustrate how we use problems to reveal the mathematics, I'm going to quickly take you through our fraction trajectory, just because I feel that it illustrates so well how we use the problems to create the awareness of fractions. And all these problems you will find in a foundation phase level classroom. Before fractions, learners need to be able to share. And this video is of a learner in early grade 1, so technically grade R. And she's asked to share, I think it's 18 beans between the 3 girls. And she's very confidently able to do it. She starts with giving 3 and then 2 each. And then lastly, she gives them 1, 1, 1. And she is very confident in being able to share these beans. She's not able to write the number sentence, but she can make sense of the situation. She can solve the problem. So before we start with fractions, we do a lot of sharing problems. And then we introduce a question such as this, where we ask them to share chocolates between friends, and they must show us how to do it. So that means we need to see a drawing. This is from a grade 2 book. So these are grade 2 children that are responding. And I hope you can see that they are very able to make sense of the fact that each one gets a full chocolate bar and they have to cut the remaining chocolate bar into the number of pieces of people that we have. Varentia also shares 1, 1, 1, and then she cuts the last one into 2 pieces. Don't be distracted by the fact that they've all got lines through them. Varentia was just showing that that one has been shared, so it's been used up. And then for the last one, she cuts the remaining chocolate bar up into 3 pieces. However, she labels it that everybody gets 1.5, but she understands they need one of the 3 pieces. And for the last question, she cuts the chocolate bar up into 4 pieces, and everybody gets a piece. I think Varentia's solution is quite telling, because in grade 2, she's already trying to write it in fraction notation when she hasn't even made sense of what fractions are. So I think as long as she can make sense of the problem, which she has, this is something that the teacher can very easily correct in the moment of reflection. You know, that's not a half, that would be 3 pieces, so we call it a third, etc. And then Shanae, very sweetly, she also solved the problem very easily, but with an added bonus. She's showing with her diagram that she knows that the pieces get smaller the more people we have to share with, which I think is quite insightful for someone in grade 2. The next part of the journey, at some point we introduce the terms or the vocabulary which we have to tell them. We have to say, if we cut something into 3 parts, we call them thirds, into 5 parts, we call them fifths, etc. This we just have to give them. And I think it's very important as teachers to call the fractions by their name when we talk about them. Because if we fall into the trap of saying 2/3 or 3/5, then the learners see these as numbers that are separate. We've got top numbers and we've got bottom numbers. So they fall into the trap of incorrectly adding these when they get to intermediate phase. If I had said 2/3 plus 3/5, well, then it doesn't become that obvious that it would have to be 5/8, because that doesn't make sense. They would have to make a plan in order to add those fractions together. So my message to the foundation phase teachers is, please use the words or the vocabulary and call the fractions by name. We do the same thing when we introduce the idea of comparing fractions. So just quickly, we would give them a series of questions, and we would share 6 chocolate bars with 5 friends, 9 chocolate bars with 4 friends, and then 7 chocolate bars with 3 friends. And then we would expect these solutions. But then we would ask them the reasoning question, which is bigger, 1/3 of a chocolate bar or 1/5 of a chocolate bar. Comparing fractions is something that typically only starts in the intermediate phase. But if we structure the activities correct, we can, and ask the right questions, we can get the foundation phase learners to start thinking and reasoning through these concepts. So by the time they get to intermediate phase, it's not that foreign to them. Okay, and then my favorite is this question here. This introduces the notion of equivalent fractions. I'm going to pause here and ask you to please solve these 2 problems as you would anticipate a learner in grade 3 would do. Okay, so how did that go? Are we done?
Yep.
Okay. So for the first one, I would anticipate the learners doing this. I share my chocolates, I've got 2 left, and I cut each one into 3.
Yeah.
Okay, then for the second one, I would anticipate someone following suit and saying, there's my 4 children, I share my chocolate bars, I have 2 chocolate bars left. So I cut each one into 4 pieces, as I've always done, and I share it out. So everybody gets 1 2/4 of a chocolate bar. But what do you anticipate, or what do you think would happen in a classroom setting? Do you think everybody would solve it this way? Or perhaps I should ask, did anybody else do it a different way? Because I think the expected result would be that somebody in the classroom would solve it like this. So they have 2 remaining chocolate bars and they would cut each one into 2 so that they have 4 pieces to share.
Mm.
And then what I love about this question is you can generate a discussion around it, saying, but who's right and who's wrong? And the learners would start deliberating, justifying that 2/4 really is just 1/2. And that's quite exciting to be part of in the classroom. They really do get quite excited about it. Okay, so that was just a quick journey through the fractions and how we use problems to develop reasoning skills. We can also link reasoning to algebraic thinking, which is the study of patterns. And I think, especially in the foundation phase, we as foundation phase teachers don't realize how we prepare the learners for when they one day do algebra and linear functions and all the different functions in high school. Patterns are the relationships between variables, which is algebra, with some form of regularity and with rules that describe them. So formulas. And they enable us to make predictions. What will happen under certain conditions, what conditions are needed for specific outcomes to occur, which links very well to the scientific experiment approach, because this is what it is. This is what we are doing. And in our program, we've got the foundation phase books, which is 0 to 12. And in these books, patterns are used to reveal the structure of mathematics, and it provides a tool for learning. And then in the higher grades, we shift and we start focusing on the developing of algebraic reasoning and thinking. So developing the formulas and understanding the deeper and meaning of the patterns. And I just want to say to the foundation phase teachers that it is so important that we focus on counting and calculating and properties of geometric shapes, because all these things are patterns in themselves, and they are the starting or the building blocks of algebraic thinking that come later. And if you can think of this pentagram, this is how it is all connected. When we have pictures that represent patterns, that's the visual representation. If we can describe that picture pattern in words, then I understand it so much better. I can also represent it in terms of numbers by using tables. And this is pretty much where the foundation phase journey in terms of patterns will end. And then we will shift gear in the intermediate phase into representing it as formula and then also as graphs. So just a quick example of that looks like. We start in grade R. Here's a pattern. What is it doing? Can you explain it in terms of words? And can you repeat it throughout up until grade 3? We also introduce patterns in the structure of tables, which is filled with lots of knowledge, which I want to get to because I want to show you just how much information you can draw from a table. So let's have a look. When we make sense of this table, we've got lions and we've got legs. So one lion has 4 legs, 2 lions have 8 legs. I hope you're noticing the doubling. So we can double to get 4 lions. That can give me 8 lions by doubling again. I'm not doubling over here, but what am I doing? I'm adding 2 lions. But if I add 2 lions, how many legs must I add? Well, I already know that, so let me use it here. And so on and so forth. I can complete my table. For the second table, I can start. So for working out 10 lions, there's various ways you could do it. The one way would be by seeing the grouping. So if I have 10 lions and they each have 4 legs, I can just multiply by 4. Alternatively, I can use the table that I've already completed, and I can say 8 lions plus 2 lions, and I can add those legs that I've calculated in the previous table. For 12 lions, I can double again. For 20 lions, I can double again. And in this way, we train the learners to make sense of the information in the table, and they complete it efficiently. And then we use the tables to solve questions. So for those two, it's pretty easy because we can just find it as is in the table. And for the others, we can calculate it by reasoning through what's happening. Okay, so then with the tables and the pre-algebraic journey, we also have flow diagrams that work with them, because eventually we're going to use the inverse operations that we foster through the flow diagrams in order to solve equations and also develop rules later on. So for those of you who are familiar with the NumberSense materials, you will know that we've got these flow diagrams or spider diagrams, and sometimes the output is missing, sometimes the input is missing. And this is very deliberate because it fosters the inverse operation understanding. And what we are trying to do is to let the activity do the work and not just tell the learners that we are busy with inverse. Let me demonstrate. We want them to solve the problem. I don't know what the output is, but if I have 26 and then I end up with 19, well, let's use the number line to make sense of it. If I count 7, so that means if I take 7 away from 26, I get 19. Let's see if it works for the next one. I have 36, I end up with 29. Does the same thing happen? Yes, it does. So that means my operation is take away 7. Then to work out the input is a different kind of approach, because this is a little bit more difficult to understand for somebody who's in foundation phase. And guess and check is an appropriate strategy to start with. So if I think of the number line, I have a number, I take 7 away, and then I end up with 59. So I know I have 59. So let's just guess. What about 53? If I have 53 and I take 7 away, does that work? Well, we would hope the learners would realize at this point that the input number needs to be greater than the output number. So let's guess again, but maybe on this side of the 59. Okay, I've overshot the mark, so let me try and get to a better result, and we will get to 66. Just to be clear, we're not going to guess and check every single time because that would be inefficient. But to start off, to make sense of the problem, this is a very appropriate strategy to pull out the number line and make sense of the problem. I'm not going to go through this one because I think you get the idea. So what we are showing them here is that eventually somebody in the class will say, if I have 26 and I take 7 away, then if I start with 19 to get to 26, I'm just going to have to undo it, which means it ends up being add. And that is where the algebraic thinking is developing, because we are showing them, maybe not saying the words because they're not ready for the vocabulary, but they can make sense of the mathematics. And that's going to build on the knowledge that they have to use a formula. And this is going to build on the knowledge of solving an equation one day. Okay. And then lastly, we've got reasoning in the geometric thinking. So space and shape also relies a lot on deductive reasoning and logical thinking. And I want to just share this activity with you. It's a pity we're not all together, because I would have whipped out my mosaic puzzles and I would have made you play with it. But for today, let's just have a look at what the activity is saying. So Sally and Clolile are trying to determine how many of piece 2 covers the same amount of space as piece 5. So what Sally noticed was, if I take 2 of this piece and I take 2 of piece 1, then it covers the same amount of space. And then Clolile says that, or he deduces from Sally's observation, that these 2 pieces must cover the same area. We can't prove it by placing it on top of each other, but we can logically deduce it. And then they go on to ask a question. So then they say, okay, if we know that the red piece and the blue piece cover the same amount of area, how many of the blue piece would you need to cover piece 4? Or what would be the same amount of area? And one way to think of it would be to build it. So I can use 3 of piece 2 to cover the purple piece. And because we've deduced that these 2 pieces are the same, then it means that the purple piece would have to be 3 pieces. I can't layer 3 pieces onto the purple piece, but I know that it is true because of my deduction. And for the little ones, this is quite a difficult thing for them to process at first because they really want the pieces to fit so that it overlays. And sometimes we as teachers just need to be patient with the process. And if they fight and kick and scream, then I guess it's okay the first time. We just have to keep on, trying to get them to understand it's about the coverage. And then piece 3, we can think about it in the same way. So there are 4 pieces, but the pieces cover the same area. So it means 4 of the red ones would cover the rectangle. And then we can give extension activities. So we've got these 2 over here. And maybe I'm going to pause here and ask if you can think about this one a little bit. So if we have the trapezium, how many of the piece 5, the right angled triangle, do we need to cover the same amount of area as piece 4? And then similarly, how many of piece 3 do we need to cover piece 7? Let's see how that goes. Do we have any volunteers? Maybe we can start with the first one, yeah. Is no one brave enough?
Please feel free to unmute your microphones, colleagues, and suggest a solution. I don't think I'm brave enough.
I don't think it's that easy if you don't have the pieces. Okay, so let's have a look. We said, or we can cover the trapezium with those 2 pieces. Great. But we can cover the blue triangle, the dark blue triangle, with the red piece in the light blue triangle. Okay. So that means we would have a half of piece 5 would be the same as the blue piece. So I hope you can see that to cover the trapezium, we would need 1 of those and a half of those. So it's 1.5. I hope that makes sense. And then for the next one, it's a similar approach. We can cover piece 7 with 3 of those. And remember, they're all the same size. And we can cover the orange piece with 4 of those. And remember, those are also all the same size. So really, what we have is we have 1, 2, 3 pieces as opposed to 1, 2, 3, 4 pieces. So if I think about the coverage, the green piece will be 3/4 of what the orange piece is. So I just think these are lovely examples or great activities that you can use in your classroom to get the learners to think logically and reason through their solutions. And if you have a set of mosaic puzzles, you could download a set and you can make your own set, and have the learners play with it and ask them the questions and create your own little activities for them to play with. So to close, if we think of a lesson structure, yes, Novosti.
So you were saying for that activity, what would help is to actually have the physical pieces that the children can manipulate. Yeah. Okay.
Definitely,
Yeah.
yes. I think even if we were workshopping this in person, we would be playing with the pieces because it just makes so much more sense. Yeah. So if we think of a general lesson structure for maths, typically we would have a mental arithmetic starter. You would have your class activity. So let's just say it's our page for the day. And then in order for the learners to complete their activity, you would give them some kind of teacher-led guidance, and then you would give them time to work on their activity. But what is very important and what I think is critical in developing reasoning is reflection. We have to make time to reflect on what the learners have done. It is a critical part of the learning process. And we also believe that with reflecting, we're developing reasoning skills because the learners are talking through their thinking and they're making sense of what they've done. But at the same time, they are also strengthening their concept understanding. And as teachers, what we can do to help them reason is to ask them questions such as, how did you do that? What did you notice? Can you explain why it worked? In this way, we get them to talk about what they've done. Then, to help them develop their understanding of the concept that they are busy with, we can ask them things such as, have we seen this before? How does that help us with this task? Or how is it same and how is it different to what we've done before or in relation to each other? And most importantly, as the teachers, we need to know what it is that we want the activity to reveal. So we need to do the mathematics ourselves and make sense of it ourselves. We need to let the activities do the work versus telling the children how to do it, because only in this way will we develop their reasoning skills. So the main ideas: reasoning is developed by talking through your thinking. So teachers having structured reflection with a clear path or knowing what it is you want the learners to notice. As teachers, understanding the concept development journey of each concept, and then using that knowledge to create new ways of learning. So we are getting the learners to be fluent and flexible. And solving challenging problems and answering thoughtful questions. So again, it's the teacher's responsibility. You need to pose challenging problems, or pleasantly frustrating problems, or there was a nice phrase to it that I read the other day that said it needs to create creative agitation, because only in this discomfort will the learners grow and progress. And then, very importantly, teachers need to ask the correct questions at the right time. And in closing, I want to share this quote with you from Erlina Ronda, which I thought aligned very well with our way of thinking, is that teaching mathematics is not about making mathematics easy, because it's not. It's about making it make sense, which it does. And I think that is very apt, because when you understand what's happening, you're enjoying what you are doing. Okay, thank you. That's the end. I don't know if we have any questions or comments.
Okay. Thank you so much for the exciting talk. I guess I'll open it up to the floor. Colleagues, feel free to unmute your microphone and make a comment or ask a question. It is a safe space. Just unmute your microphone.
From the Overberg side, I just want to say thank you very much for a very, very pleasant and very, very informative session. I just had a session with a few teachers on patterns on Saturday, and I wish I saw your presentation before that. Yeah, so thank you very much. I really enjoyed it as well.
You're most welcome, and thank you for the feedback. Just get in touch. We are always available to lend a hand or, talk through some problems. So we love nerding out when it comes to maths. So please just get in touch. Thank you.
Okay, awesome. Thank you, Sandra, for the comment. Colleagues, anybody else with a question? We still have about 2 minutes, 3 minutes to chat before the next speaker.
So maybe what I can do is I can share this problem with you. I know I said I would be done, but I will leave this problem with you, and then email me with your solutions, and we can talk about, different strategies and how we can elevate this for your class. So the problem goes, Bonky makes 3-legged stools and 4-legged chairs. Last month he used 72 legs altogether, and he made 3 more stools than chairs. So how many stools and how many chairs did he make? And this is a lovely little investigation for the learners to puzzle out, but for the teachers to puzzle out as well. So my email, if you would like to send it to me, would be Stephanie, STEPHANIE @brombacher.co.za. I hope to hear from you.
Okay, beautiful. Thank you.
You're welcome.
And any more questions or comments, colleagues, before we wrap up this talk? Okay, my colleague is making a comment. She's saying it was lovely. It was a lovely talk. Thank you, Rose.
Awesome. Thank you very much.
Okay, so if there isn't any more questions, I wish to thank Stephanie for the intriguing talk. It definitely got myself and Rose thinking about some of the things that we've taken for granted, I guess, as adults and as maths and science teachers. And I hope our dear colleagues probably also had a bit of thinking to do as you were talking to us. That being said, thank you so much, and to your team, and for availing yourselves this afternoon. It's always beautiful to share such platforms together.
That's awesome. Thank you very much. And thanks again for the invite. It was lovely to be here. Thank you, everybody.